Okay, I think we'll get started. So today we're going to talk about moment of inertia. And so before we do that, let's recap what we've seen so far now with this relationship between our linear motion and our circular motion or rotation. So position, which we often call x or r, in this case we're calling s because that's the arc length along the motion on the rotational path, is analogous to angle, and the relationship there is s is equal to r theta. Now I'm putting a vector over the theta to represent are we going clockwise or counterclockwise. So counterclockwise is the positive convention usually. You can check your physics book that you're using. And the clockwise is negative convention. But we see here, and we'll see this as a common theme, the radius of that circular path amplifies the angle. So if we have a longer path, and we're at a given position, we're at a larger arc length starting from the x-axis. Then angular velocity is related to velocity, again leveraged by r, and likewise for acceleration. So we see this very common theme here. This more or less translates over to force and torque. The one thing we do have to be careful of is that we're talking about the lever arm. Now, we saw that there's two ways to think about that. We can use R and then the perpendicular component of the force, or we can use this lever arm idea that we talked about last time, and the full force. And whichever you use would probably be dictated by the situation. Sometimes it's easier to think about it one way, sometimes it's easier to think about it another way. Today, we're going to add one new thing here. Actually, two new things. We'll be able to add to this an additional thing, and that is mass and its relationship to moment of inertia. So moment of inertia plays the role of mass and in the rotational dynamics, and the relationship is this. All right, so let's get into our moment of inertia, see where that comes from. So let's take our relationship right from the board here. So we'll look at acceleration. And the reason we're looking at acceleration is because we want to get to this idea of mass and its relationship to moment of inertia. And we know acceleration is related to force via the mass from Newton's second law. So we have the second law here, F equals ma, a being the linear acceleration. Now, there's definitely a point of possible confusion here. So let's pause a bit and make sure that you understand what acceleration we're talking about here. So we're talking about the acceleration causing the rotation, right? So this is an acceleration that is tangential to the point on the curve. And I think it's also important to look at it as, say, rotating a molecule. Now, of course, these are essentially the same system, but sometimes it's a little easier to think about it this way. We need to rotate this molecule, or whatever object this is, and we're going to apply an acceleration to cause that rotation. Now, what are we used to from before? We're used to the idea of centripetal acceleration. That's not the acceleration we're talking about here. There is indeed a centripetal acceleration and thus a centripetal force, but let's consider the action of that force. So we have the acceleration straight downward. This is our radius at that point. We can convert this acceleration via the mass to force via Newton's second law. And so our force is in this direction. So our centripetal force is in this direction. And so two ways to look at it. There is no perpendicular component to that centripetal force, and therefore it does not contribute to torque in any way. And there also is, from the other perspective, the lever arm here would be 0. So indeed, there is centripetal acceleration in these problems and centripetal force, but we're talking about the force applied here. Right? Now, if we have a force applied here, then in this direction, tangential to the path, then we can define our torque as well. So we know from last time, torque is leveraged by F. And notice here now, we're tangential, so this is a special case of this over here, where the lever arm and the radius are the same here, because the force is directly perpendicular to the radius. All right, now we just need to do some substitution here. So let's substitute this into here. So we have torque equals R times mass times acceleration. That's force. So that's just coming from this equation directly. But then what's our acceleration? Let's substitute this into here. And so now we have mass times R times the angular acceleration, because the acceleration is leveraged by this factor of R here. Now we can collect these. So we have mr squared, and of course we could just leave it as that, but that's something that is convenient to define, and so we do that. And we say this is defined as moment of inertia, and usually given the symbol capital I. And thus we have tau equals I times alpha there, or torque equals moment of inertia times alpha. So basically, this is the second law for rotation. Now, of course, we don't have to box that off and write it, because we can derive it directly from the second law. But that's the second law version, or how it plays itself out. So we can add that. See if I've got, should have left a little more room here, but let's add that to our list here now. F equals ma. Tau equals I alpha. All right, so we're really starting to see these analogies between the linear and circular motion. Now, what about more complicated systems where we have multiple point masses? Well, the moment of inertia simply adds. So we can label each one of the masses, 1, 2, 3 in this case, and then each of the radii, and then the overall moment of inertia is just the summation of each of the individual moments of inertia for each point mass. Now the radius, I should be a little more careful here. The radius is measured relative to the center of mass. Or a pivot point. So there could be a couple of different cases. So if it's just a free rotation and we want to get the moment of inertia, then we're about the center of mass. If we're fixed, if we've got something else and say have a pivot point here, let's call that a pivot point, then we would measure relative to the pivot point. And that would be the sort of straight line distance to the pivot point. So if M3 was actually attached to a pivot point, then we would calculate this differently. It would be based off of the pivot point. Again, if it's a molecule freely rotating, then we calculate the moment of inertia off of the center of mass. All right, well, what about objects that aren't point masses? So if we go beyond molecules and get up to bulk substances, and they need to rotate, well, a general shape here, maybe I should put some perspective here, is complicated, and it really is a calculus, what would be taught in a Calculus 3 course. So we won't go into it here in this introductory sequence of courses that we're laying out right now. But if you've had some calculus, you may have started to talk about this, particularly if you've had several calculus. You might go back to your calc book and see how a general moment of inertia is calculated. Now, your physics book, regardless of what book you have, whether it's a calc-based or algebra-based, will collect some formulas that come out of this calculus calculation for various important shapes. And I've just listed two here. A sphere. So a sphere of mass m, capital M, will have a moment of inertia formula that is I equals 2/5 mass r squared. So let's get an intuitive feeling for that. We certainly wouldn't want mr squared, because that would be saying all the mass is on the edge of the cylinder, of the sphere. But it's a solid sphere, like a wooden ball or a steel ball bearing. So some of that mass is closer. And so we think this 2/5, we have to think of that as sort of accommodating for the amount of mass at every given distance. And of course, we can't intuit the 2/5 unless we've done some calculus there. But that's the formula. A cylindrical rod rotating about the axis of symmetry, so rotating this way, if this does actually have some thickness, and rotating this way. Moment of inertia is 1/2 m, m being the mass of the whole thing, r squared. You might want to rotate this way. If this is L, then it turns out that it's 1/12 L squared. So look at the formulas in your book, practice a few problems with these extended objects as well. All right, so that is moment of inertia, important for rotation problems. We'll see this become important when we talk about angular momentum down the line a little bit. So just like mass plays an important role in the definition of momentum, and then of course momentum is really important because of conservation of momentum, moment of inertia will play a similar role for angular momentum. And we know from the very first lecture in the course that angular momentum is a key quantity because it is also conserved. It's also a conserved quantity. So we'll be able to add one more line to this that includes momentum and the analog in rotation, angular momentum.